I'm Wilka Carvalho, and I will be presenting this work with my collaborators at KAIST, DeepMind, and Google Brain. So I think the driving question of this work was, how can we teach machines to perform real-world tasks? And this is things like making coffee, making toast, and really a variety of other household chores, like making breakfast, making dinner, throwing out the trash, etc. And so in this work, we focus on teaching AI to perform household tasks using reinforcement learning. You might be asking yourself, you might not be, what is reinforcement learning, or RL, as it's commonly referred to? It's basically a broad class of algorithms that enables an agent to learn behavior by acting in the world. And so it acts in the world. You see my pointer? Yeah, you can. It acts in the world state changes, it gets some reward back, and based on this, it learns how to act. The reward might be 0, or it might be positive or negative, but over the course of many interactions, it learns what's good and what's bad. So why use reinforcement learning? This is probably most obvious in contrast to supervised learning. So if we were to tackle this from a supervised learning approach, we might define what are good actions at different time steps. And that can require a lot of engineering and can be difficult to get. But here, we only need to define a source of reward. And from that, the agent can learn how to behave. And this method has seen a lot of success on related tasks like robotics control and navigation of embodied agents. Okay, so I've introduced reinforcement learning. Now, how do we model learning to perform household tasks using reinforcement learning? Emphasis in a 3D environment. So there are a few things that we have to define. The first thing we have to define is the state representation of our agent. So the agent is going to have some egocentric observation. This is a fancy way of saying first person. It will know what are the objects in its scene, or like the bounding boxes of them. So it might see what corresponds to the egg and to the tomato, etc. It won't know the label though. And it'll also know where on the map it is. So it's like XYZ position or something like GPS. We also have to define a reward function. Now, for this, we can just have it be task completion. So for example, for the task of slicing bread, it'll get reward when the bread is sliced, right? So it has to do all these actions, and then bread is sliced, +1. Now the last thing to define is the action space. So the agent can move its body, it can move forward, backwards, left and right, and it can move its head to shift its perception, up, down, rotating. And then a critical part of this, or a more interesting part of this, is that the agent can interact with objects. So there are some interactions it can do in general, like slicing, picking up, closing, and it can apply these to any of the visible objects. And so the action space there is a cross product of these space interactions and the visible objects. Okay. So in order to teach an AI to perform household tasks, let's look at some of the characteristics of household tasks in 3D environments. So perhaps the most notable one is that this is a sparse reward setting. And this means that the agent rarely experiences reward as a reminder when the task is complete. To get some intuition for why this means it's a sparse reward setting, let's look at another characteristic, which is the branching factor. So the branching factor corresponds to the number of actions that the agent can take at every time step. Here I show the world state with its globe, and I show the actions over here. Now as a reminder, the actions encompass interactions. This is a cross product between two sets. Basically, you're multiplying the sizes, and this can grow to be really large. And so we can have an action space like in the hundreds. And what this leads to is this challenge, the challenge of having a giant state action space. For some intuition about what this means, I have this little simple diagram of a state action space. I represent the agent's starting state with this S. Now, in this state action space, I represent the part that will give the agent a reward with this small green square, right? So it's a very small part of this large space. And And because of this large branching factor, even if the agent is going towards the part of the state action space that will give a reward, it can easily deviate off and go somewhere else where it will not get any reward. And for an example of this, let's use the example of the task of slicing bread. On the way to slice bread optimally, you have to go to the drawer, pick up a knife, go to bread, slice it. On the way towards that, which is over here, it might just completely bypass that and go to some other part of the room. It might pick up other objects, and when it has one object, it cannot pick up another, and this might make it go further and further away from being able to get the reward. And so key takeaway is that a large state action space can lead the agent away from reward. Another challenge is that of recognition. So let's look at seeing bread here. I hope it's clear. The agent may not recognize that the bread is the same object from different views. I'm calling this perceptual noise. So it has to recognize objects from different views. Skipping over these things. So we have to overcome this sparse reward problem. A common method to do this is to define a systematic exploration method around state actions. And a common way to do this is to define intrinsic reward based on the novelty of state actions. And so and a simple way to do this is to just have novelty around object interaction count. And so the reward can be 1 over the square root of object interactions, which goes to 0 over time. Interesting. So one thing, because of perceptual noise, this can actually lead to overexploration, because the agent may not recognize the novelty of picking up bread is the same as the novelty of picking up bread because of the different angles. And so we have to solve this perceptual noise problem. So our solution to this is object memory. The agent keeps a memory of the object images it sees, and this enables it, as it sees objects in the environment, it uses a recognition function to map them all to the same memory slot. So now it's view invariant. And this addresses the perceptual noise problem. With this, now you can maintain a count of object interactions using the memory, and we can use the same reward function, the reward that I mentioned before. And now, because the reward is around unique object interactions instead of object view interactions, this leads to object-oriented exploration. Going somewhat briefly over this, how do we train this agent to actually have a view invariant recognition function? Because it doesn't have this from the start. So it's actually very simple. It acts in the environment. As it does, it adds new object images to memory. This is based on the distance of an object image of its embedding or the features of a neural network to the ones in the memory. It also adds all observations to a replay buffer. This is common practice in reinforcement learning. And then it uses the memory as labels. Long story short, it learns to put similar objects close together in some embedding space. I'm running short on time, so I will go very quickly through experiments. Basically here is a core RL algorithm. There I have also correct object interaction reward, but no learning representations. They do about the same. Intrinsic reward isn't as helpful without recognition problems solved. Our model, we use memory to count object interactions, but also to learn representations. You get much more reward over time. So I'm going a little bit quickly through this because we're short on time. And then the last part, we also compare against counting object views instead of individual objects. This is the worst. We hypothesize because of overexploration. Counting object views leads you to overexplore and not really search the space. I think I'm out of time, so very quickly, view invariance enables exploration, which is good for household tasks. Thank you to my collaborators, my advisors, funding sources. Thank you for Black and AI for having this event and for inviting me. I appreciate it. That's it.
Thank you. Great presentation, by the way. I was just interested more in the deep Q-learner side of it.
Sure.
I figured where you were going, you had to use some kind of function approximator, just due to the amount of states that you had.
Sure.
What kind of structure did you end up figuring out was best for that? And is there any future work of going into more future neural network architectures?
Yeah, so this is totally a fully neural network model.
Right.
in terms of the details of that, because we have a variable number of actions, it's actually a little bit tricky. So I think we should talk about it more offline, but basically you could, it's like vanilla DQ network, but at the object level instead of at the scene level. And we could talk more about that offline.
Yeah, I'll find you after this. All right,
but thank you for the question.
No problem.
Great, and our last question right here.
So I'm curious around so it's kind of a two-pronged question. The first is like, what was the motivation behind doing this type of technology and creating a bot to be able to do these type of, tasks like slice bread and scramble eggs?
Yeah, humans are great at these tasks. But I think right now, so humans are great at these tasks. It's not clear that AI is. And one thing that I didn't get a chance to really highlight here is that this is in the context of sample efficiency. So a lot of the time in kind of like environments like this, you have to collect many samples, like in the millions. And we were like, hey, how can we like collect less than a million and try to do well? Because humans are pretty good at that. I'm driven a lot by human ability.
So is there any consideration to how this type of technology and doing home tasks within the home has an impact like on the family, or has an impact on culture and how we experience, your mom, making you breakfast instead of S-362, doing it for you?
Sure. That's a great question that I'd love to chat more about. It's probably like not in the scope of this thing, but like brief comment on that. Yeah, I imagine that culture will adapt to, culture always adapts to technology, right? So I don't know if that would take away necessarily from like community and cultural things that are based around, let's say, cooking, for example. But it's interesting to hypothesize like how that would transform family structures and community structures.